Question 21. A circuit is set up as shown. The internal resistance of the supply is negligible, and we're asked to find the power dissipated in the 4 ohm resistor. The word dissipated means lost. Now, when we look at the 4 ohm resistor, we realise that it's connected in parallel with the 6 volt supply. We can see that there. So that's going to have 6 volts across it. We can put in a voltmeter there, and there'll be 6 volts across it. Now, if we're looking for the power equations, we know that the power equation is as follows: P equals IV. We can have P equals I squared R from the relationship sheet, and we can finally have P equals V squared upon R. So we know the voltage across the resistor, we know the value of the resistor, so we can find the power dissipated in it. So power equals V squared, which is going to be 6 squared, divided by resistance is going to be 4. So 36 divided by 4, and the power dissipated resistor has got to be 9 watts, and we're dealing with 2 figures here. We do 9.0 watts. So our answer to that question is going to be D. Question 22. 4 resistors are connected as shown. We have 3 resistors in parallel and 1 series resistor. The total resistance between X and Y, and we're given our 5 choices. Okay, between this part of the circuit here, we'll dot round the circuit, that's the parallel part, and we've got the series part here. So 2, 4 and 6 are not easy numbers to deal with, as in the simple hack of finding half and a third. We have to rely on the formula. So 1 upon RT is going to equal to 1 upon 2 plus 1 upon 4 plus, of course, 1 upon 6. Okay, if you're doing a calculator, you can do that quite easily, but I'll just do it with the common denominator. Common denominator here turns out to be 12, because 2 can get 12 6 times, so we'll get 6 times 1 is 6. 4 can get 12 3 times, so it's 3. 6 can get 12 twice, so we have 2. So we have 1 upon RT is going to equal to 6 plus 3 plus 2 is going to give us 11 upon 12, and that implies that RT of the parallel part is equal to 12 upon 11. And we do that on my calculator, we get a value of 1.09 ohms. So now we have to add on the 8 ohm resistor in series, and therefore we have the total resistance, if we can call it that. Total resistance is going to be the 1.09 from the parallel part plus the 8 ohms from the series part, 8 ohms like that, and therefore we get a total of 9.09 ohms. So the total resistance is going to be equal to 9.09 ohms, and we can put that to 2 significant figures, and our total becomes equal to 9.1 ohms. So we're looking for 9.1 ohms, and the answer to that will be C. Question 23 and 24. We'll start with 23 first. It says 1 ampere is equivalent to, and it gives you the following responses. We've got to remember that the current I is the current, and that's equal to the charge divided by the time. It's the rate of charge flowing through the circuit. If we look at the units for that, the units for the charge are going to be the coulomb, and units for time is going to be the second. So we're looking for a coulomb per second. Coulomb per second for current. That's the standard unit, and that's going to give us an answer of coulomb per second. It's going to give us an answer of B for that one. Now let's take a look at question number 24, and it's a standard one once again. It says the following. It goes, the 220 microfarad capacitor is connected to a 12 volt DC supply, and the maximum charge that can be stored in the capacitor, and we're given the responses. Well, we know the definition of a capacitor. Capacitor C is equal to the amount of charge Q that can be stored for a certain voltage. We know the voltage, we know the size of the capacitor. A wee bit of rearranging gives us Q equals CV, and therefore we have the following. We have the value of the capacitor, which is 220 microfarads, 220 times 10 to minus 6, multiplied by the voltage, 12, and we do that in our calculator. We end up with 2.64 times 10 to the minus 3 coulombs of charge. Obviously we have to use our significant figures, so we're going to get an answer of 2.6 times 10 to minus 3 coulombs. That's going to give us an answer D. Question 25. The frequency f of the sound produced by a vibrating guitar string is given by the relationship f equals 1 upon 2L times the square root of t divided by mu. And we're told what these symbols stand for. Capital L is the length of the vibrating guitar string in meters. Capital T is the tension in the guitar string in newtons, and mu is the mass per unit length of the guitar string in kilograms per metre. We're given the vibrating guitar string produces a sound with a frequency of 160 Hz when the length of the string is 0.64 metres. The mass per unit length we're given that as 1.5 times 10 to the minus 3 kilograms per metre. I'm being asked to find the tension in the guitar string, but as you can see the tension is stuck inside that square root sign, so we have to extract that tension or change the formula for tension. Okay, we start with the formula. We have got the frequency f is going to equal to 1 upon 2L times the square root of the tension divided by mu. I'm going to multiply both sides by 2L to get rid of this fraction here, so I'm going to end up with 2L f is going to equal to the square root of t upon mu. And if I square both sides, I'm going to get rid of the square root inside this. So the square root of 2LF is going to be 2LF all squared. That's going to equal to t over mu. And I can see now I've got tension divided by mu, and I can get tension on its own by just multiplying by mu. 2LF all squared, so therefore the tension becomes equal to mu times 2 times L times F, and we'll have to square that particular bracket. So now I've got the value of the formula for the tension. Now all I have to do is put in the numbers. So tension T is going to equal to, first of all, mu, which we're told is 1.5. 1.5 times 10 to the minus 3. And multiply this bracket by 2 times the length of the guitar string, and the length of the guitar string is 0.64, so that goes in there. Multiply by f, the frequency, which is going to be in this case 160, and don't forget to square it. So it boils down to a calculator problem, and you just plug those numbers into your calculator, and we end up with a value of the tension to be 62.9 newtons. Now we can round that to two significant figures because that's what we've been using all throughout the question, and therefore we find out the tension T to two significant figures is 63 newtons. So we're looking for that in our response, and we have an answer here of C, and that ends paper 1 of the 2026 Higher Physics.